Vanakkam, Namaste, Namaskar, and welcome back to Jal Prayag again. My intention was to continue with the definitions which we were talking in the last video regarding basic stability. But I got a suggestion from someone that I should take one topic before I continue. And the topic was flotation. I agreed because of a few reasons. And I also felt that if I make a small video regarding flotation, understanding the definitions of displacement and rest of the features in your basic stability becomes much more easier. So in that process, I'm going to start off with the topic called flotation today. Once I finish this, I'll continue back on the definitions, and you will see it will make much more sense in a sequence. So let us look what is flotation. For me, a basic question arises: why should an object float, or why does an object float? This question is actually taught to you somewhere in your school time, somewhere in 8th and 9th class physics. But anyway, I always say that the whole stability is also physics, is a continuation of physics. So let us look at some basics about my flotation, which is involving my ship, as well as in physics as well. Now, there were two reasons why I agreed to make this video on flotation. The first one was why a ship's weight or a mass is called displacement. So that you can understand once I finish this explanation on flotation. And the second is, it is a kind of byproduct of the same displacement principle, where I can calculate tons per centimeter, which is also an important feature used in your stability. So understanding flotation will give you an insight to why displacement is named for weight of ship, and then how it can lead to remaining part of the stability also. Let us look at a very common logic, let us say school logic. Why does an object float? I can give you a simple reason telling that, let us say I have an object lighter than some other object which is heavier. And if both of them come into contact, you will see the object which is lighter is going to float. If not, then it is going to sink. Now, just by telling lighter or heavier, I'm talking about a weight. But that is not the right way to talk about flotation principle. I should involve something called density. All of you know what is the basic definition of density. Density is mass by volume. So I should be talking about density rather than just telling whether object is heavier or lighter. So now if you see, I can rephrase the same sentence. I can say that if an object is more denser than the other, it is going to sink. And if the object is less denser than the other, it is going to float. Now, you need to understand that gases and liquids are also fluids. So that means if you ask me, even air is also a fluid. I'm going to talk about more of liquids. Why? Because we are dealing with stability where a ship is floating in water. So I'm going to deal with liquids, but still they are also fluids. Now, a simple example, daily life example for you regarding floating can be oil floating on top of water. And we can say that if you throw a piece of wood on the water also, yes, the wood is going to float. But when you start dealing with ships, we don't use the concept of density. even though it holds good, but we don't use the concept of density. We use a slightly different concept, and that is where this flotation will lead finally for me to talk about displacement. So for you to start understanding the principle of flotation, the first thing you should understand is what is Archimedes' principle or theory. It's very, very simple. It says that any body which is fully or partially immersed in a fluid, this body suffers a loss of weight. And that loss of weight is equal to weight of the fluid displaced by the object. Displaced means you can call it pushed by the object. It just took over that place, pushed by the object. So this is something, the foundation of the whole principle of flotation. Loss of weight is equal to weight of the fluid displaced. Let us understand what do you mean by fully or partially immersed in a fluid. I'm just going to show you in a small picture. Let us say I have a container, a big container, and a water inside the container up to the blue level. I'm going to, let us say, hook up an object. Let us say it is a rectangular object. And I keep it like this, hooked up. I can call this partially immersed because the full body is not into the water. Similarly, I can show you one more example. Same object is hooked up, but this time, this I can call as fully immersed. So this is the meaning of partially immersed and fully immersed in a fluid, and the water is the fluid. Now, let us see how we can measure the weight of the water displaced by this object. You can see that is a part of this Archimedes principle, weight of the water displaced. You can see here, if I have a separate container, just for the sake of explanation, I call this overflow container. And I connect it with this big container with an overflow pipe. That means anytime the water level in the big container reaches this overflow pipe, it is going to flow down to this overflow tank. And maybe I can measure it. I'm going to take an object. Let us say I'm still hooked onto this object by a crane. I slowly lower it. I bring it up to here. Now it's very evident that this object has taken over some space of the fluid. So that means it is going to push. And you can see in this container, the water can neither go on the sides, any of the sides, but it can rise. So when it rises up, it is going to go to the overflow pipe and it is going to fill this overflow tank. A quick reasoning, what you can see is, if I ask you how much is this overflow water which is in the overflow tank, how much has it overflowed? You can very simply say that this is the amount. Now I've shown you a two-dimensional picture. You should imagine on a three-dimensional shape of a rectangle. So how much was the water which overflowed? I've shown you both of them with the blue color. This is the basic concept for you to understand something called fluid displaced. So this is the amount of fluid displaced. Now I'm going to see the next part of Archimedes principle, which is called loss of weight. Let us see how we can measure the loss of weight. Right now I've shown you how you can measure the water displaced, and we can measure, weigh the water displaced also. I can use any methods like a weighing machine or something, sensors or whatever, it can tell me the weight. So let us look at loss of weight of the object. I'm going to show you next diagram. I'm again mentioning Archimedes principle in a simple single liner. When the body is fully or partially immersed, it suffers a loss of weight, and that is equal to the weight of the fluid displaced. Archimedes principle, for me to explain, I need not have an object floating. It can be just immersed, that's it. So I'm going to show you only immersed object. I'm still not coming to the floating concept. Same big container and the overflow container. Let us say I have an object which is 10 tons, which weighs 10 tons in air. and I'm holding with a crane, and crane has got a weigh measuring instrument. It could be spring balance or anything for the sake of explanation. And obviously this spring balance is going to show me 10 tons. Why? Because the object is also 10 tons. Now I'm going to slowly lower it down with the crane. Let us say this is a stage 1. You can see that object has gone inside the water, so it is partially immersed, and very evident that it has displaced some amount of liquid. So that amount of liquid will overflow and come here. At this stage, if I look at the spring balance on the crane, you will see the weight would have reduced. For example, let us say it was 8 tons. Now, something for you to realize is what is the loss of weight right now? What is the object feeling as if it has lost a weight? It is basically 2 tons. Now, what is the use of this overflow container? This overflow container is going to also show you the same 2 tons. Now I'm going to lower it more. Stage 2. Again, more overflow. Again, the spring balance is showing me some different weight, which is 6 tons. And it's very evident that the loss of weight is 4 tons. That means this overflow tank is also going to show me 4 tons now. Similarly, let us see one more stage. Again, some overflow. Again, the spring balance is showing me lesser weight. So it is showing me 4 tons. So the loss of weight is 6 tons. So my overflow tank is showing me 6 tons. So this is what is your Archimedes principle. You can see the loss of weight is equal to the weight of the fluid displaced into the overflow container. So this explains a simple way of understanding the Archimedes principle. For me, this Archimedes principle is just to start off with the concept and lead you to a new principle called law of flotation. The word flotation itself means that I'm already floating. And it's quite obvious that a ship, what you're dealing with, I want it floating. So that is my intention. So I'm going to slightly modify this Archimedes principle, and I'm going to show you side by side both the principles, how it leads, Archimedes principle leads to law of flotation. Okay, let us understand that whenever I say object is floating freely, that means let us say a piece of wood or whatever you have thrown in water. If it is floating, it is actually feeling weightless. That means it feels as if I have no weight, which also means that apparently it has suffered full loss of its weight. That is why it feels that I'm weightless. Actually, it has got some weight, but it feels as if it has lost a weight. And whenever an object suffers full loss of weight, then it is called floating. So this is the same thing which I've written. If an object is feeling weightless, that means zero weight. It means that it has displaced water equal to its own weight. And when you try to link it with Archimedes principle, loss of weight, please remember, is the full body weight. And it is equal to the weight of the liquid displaced. So I can quickly give you a small write-up on principle of flotation. I am already floating. I am feeling weightless. That means I have suffered full loss of my weight. And that full loss of my weight will be equal to the weight of the liquid displaced, which means weight of the liquid displaced is also equal to the weight of the object. Now, this is what tends to give me the idea of displacement. Let me show you again the experiment which I showed you based on Archimedes principle. But this time I'm continuing from the Archimedes principle experiment to the law of flotation. Okay. In Archimedes principle, I had mentioned there is no need for you to float to explain Archimedes principle. You can just be immersed partially or fully. So you can see these 3 stages which I had shown you earlier, they're all partially immersed. And I'm going to continue this stage. Let me continue with this experiment. Let me lower the crane more. to this next stage. So that means I would have had more water coming onto the overflow tank. And in this stage, let us say the crane spring balance is showing me 0 tons. Now please see what is the loss of weight. The loss of weight is 10 tons. That means the liquid displaced is also 10 tons. This is the condition where I can convert the Archimedes principle into the law of flotation. That means I'm floating freely. Now I can remove the hook from the crane. I can just remove it and this body will float freely. A floating body feels weightless because it has displaced an amount of water equal to its own weight. So that is what is the last part of this experiment, which says loss of weight is 10 tons. And when you measure the overflow tank also, it is 10 tons. I'm going to show you 2 more examples based on the flotation to confirm this. Let us assume again, similarly, this tank is there. And I again have this overflow, and I'm going to take again a crane. Let us say I have a crane. This time I'm going to purely give you the law of flotation. That means the object is floating. So I have to show you the object is floating freely. Assume the weight of the object in air was 10 tons. I kept on lowering it. And I came to a stage where this object started floating freely. That means the crane was showing me 0 tons. So I took off the crane, the hook. You can see it is partially immersed and it is floating. You will realize that the crane is showing me 0 tons and the water here is also measuring 10 tons. So this is floating freely. I'm going to take one more object, let us say a heavier object, and I consider that 15 tons. So when I kept on lowering, I could get a reading of 0 tons only when it was fully immersed. Obviously, I can see that this water is also 15 tons. You can see these are 2 cases, both the cases of floating, but one is partially immersed and one is fully immersed. But both of them are floating. Right now, they are both floating, which is evident because I've already displaced water equal to my body weight. First object was 10 tons and the second object was 15. Both of them are floating. Now, please look at the relation between Archimedes principle and flotation. All I can say is there is one common term between or within these 2. Both of them are marked with a green color in the 2 equations, weight of the fluid displaced or weight of the liquid. If I take it off, do you agree I can say loss of weight is equal to weight of the object as far as object is floating? The loss of weight is equal to weight of the object as far as the object is floating. And if it is floating, it has displaced the amount of water which has pushed it out, which the object pushed out, is equal to the weight of the object. Now, with this, do you agree that a body floats freely? It suffers apparently full loss of weight. It is an apparent loss. It is not a real loss. Please remember, body's weight is still there. It is feeling a loss. So it is called apparent. It is as if a force is pushing us from water in upward direction against the body weight. So if these 2 forces are equal and opposite, they cancel each other and the object can float and it feels weightless. We can interpret a few things based on whatever we have seen. Let us look at the first interpretation. That means the object's density is less than the water density so that it can float. Example, an iron ball will sink because its density is more than the water. A ship can float if its density is less than the water's density. The second concept I give you is the force of weight is equal to force of buoyancy. These two concepts, weight and buoyancy concept, I'll be talking in a different module, so I'm not going to explain much on this. But let us look at the last one, which is more important. Whenever we deal with the ship, we don't directly relate to its density, even though I mentioned in the previous slide. But we mention it in a different way that is based on Archimedes principle as well as your law of flotation. If a ship is able to displace an amount of water which is equal to the ship's weight, then it is going to float. So this is what I've written here. If a ship can displace water equal to its weight, it will float. But if she cannot displace water equal to its own weight, it will sink. I'm going to quickly show you a concept, which I call it sinking concept, just to understand, because if you know why it is floating, you should know why it is sinking also. I'm going to continue a similar experiment. Let me show you here. I'm going to slowly immerse an object. Let us say the object was 10 tons of some other shape. The shape depicted here is only just for example, some other shape. It was 10 tons. Same crane was there. A weighing machine was there on the crane. I started lowering. And let us say in this condition, it is partially immersed. It displaces some water. And at this time, the crane is showing me 4 tons. So that means the amount of displaced water is going to be 6 tons. Now continue the experiment. Let me lower it more. Now it has reached a condition of fully immersed state. That means it has pushed the maximum amount of water it can push. Why? Because it took over the place of the water. It is as if telling that you had a seat and somebody came and pushed you and he sat down. So this object has pushed you out. So the water has been pushed. You can see that, let us say in this condition, I still have the crane showing me 2 tons. If the crane shows me 2 tons, it also means that water displaced is only 8 tons. Now you should realize something. This body is fully immersed. That means it has got no more shape for it to push any more liquid. It has got no more shape, or you can call it no more underwater volume. And the amount of liquid it got pushed was only 8 tons. That means it was unable to push its full weight of 10 tons. In this condition, you can say that it will start sinking if I remove the hook of the crane. If I just take off the hook and leave it free, this object will start sinking. In other words, I can write it like this. Floating means the weight of the water displaced is equal to weight of the ship. Sinking means the weight of the water displaced is less than the weight of the ship. Now, when can this happen? This can happen because of the shape. Size and shape, whatever you want to call it, this can happen. So a simple example is a small iron ball. Let us say it's a small ball bearing. And all of you have done this experiment, or a stone. If you throw it, it is directly going to sink. Why? Because the shape of that iron ball did not have enough volume to push the water which was equal to its weight. So this is where I start giving you a new concept. I've shown you the same experiment somewhat here. The ship is a huge structure. It has got enough shape to push the water, which is equal to its own weight. But a small iron ball or a small block of steel does not have enough shape or the volume to push equal to its weight. So I'm going to come to this explanation now. If a ship is floating freely, it suffers full loss of its weight. That means the weight of the water displaced is equal to ship's weight, and hence I can call the ship's weight as the displacement. That means the weight of the liquid displaced. So hence, from now onwards, in my stability, I will never call it as weight of the ship or the mass of the ship. I always call it displacement. We can calculate the weight of the ship or weight of an object, any other object also, with this modified formula of a simple mass equation. We all know mass is equal to volume into density. It's a simple physics equation. So how can I modify this for displacement? I say mass is equal to displacement. Then the volume in the equation, I call it underwater volume of the water displaced. And the density is density of the water which is being displaced. You can see this will lead to this equation and it will end up in tons. But you should realize that this equation involves only external factors, nothing of internal factors of your ship. Both underwater volume, which I mentioned in displacement equation, and the water density I have mentioned is both external to the ship. It is not internal. But you need to realize that any other object, I can parallelly use the same formula, mass is equal to volume into density, with internal factors. So what do you mean by internal factors? Internal factors means density of the own object and the volume of the own object also. And you will see these two have to be same. I'm going to show you a simple concept which is used in all your problems. Let us say I have a rectangular piece of wood. And I'll show you that how to prove that displacement is equal to m. I'm going to show you with pictures. Let us see this. I have a rectangular piece of log. And let us say it has got a length called L and breadth called B. I've shown you on the left-hand side, this object is in air. And the right-hand side, I've shown you this object is floating in water, the same object, exactly the same object. So obviously the mass has to be same. How to use a formula which is internal and how to use a formula which is external. Let us quickly see the internal formula. Internal formula is volume of the object and density of the object. So here, for you to calculate volume of the object, I can say L into B into H is the volume. And let us say this wood had an RD of its own of 0.8. So I can use this formula and calculate. You can see it is L into B into H into RD of the object, which is 0.8. I can find the answer. Now the same piece of log, let me say I'm just throwing it in water. It is going to float. And you can see I've shown you the water line with green color. Let us see how I'm going to use the second formula now. And both this M and displacement have to be exactly the same. So displacement can be calculated using underwater volume. Please look at the log, length and breadth does not change, but this is the underwater volume part of it. So it is called a draft. And let us say I'm floating in a water of 1.025, which is seawater. And if I make an equation, it is length into breadth into the draft, into the density of the water. So this is the difference between internal formula and the external one. And you will realize both displacement and m, which is the mass of the object, they are both same. And this is the concept used in all future calculations. And this concept of displacement will help me in the further definitions also in stability. And I'm going to use the same concept for me to explain about TPC also. So I hope this principle of flotation was a simple one to understand. And when I make the next video, I'll continue on the definitions. And for you to understand on the basic level, it'll be much more easier on a sequence. I'll catch you soon. Till then, keep watching Jal Prayag. Namaste and Vanakkam.